The narratives that you are about to see are fictionalized scenarios. Names, characters, businesses, places, events, locales, and incidents are either the products of the author's imagination or used in a fictitious manner. Any resemblance to actual persons, living or dead, is purely coincidental. The use case number 2 narrative demonstrates in-flight modifications to intent in a high-density airspace, using first, broadcast remote ID for rogue or contingent UAS, and second, supplemental data service provider services for detection, alert, and avoidance of manned and unmanned traffic. Following the successful de-confliction of the various flight plans submitted in Blacksburg after the storm, the environmental and agriculture surveys, media activity, search and rescue missions, and hobbyist drones are airborne by 6:50 a.m. At 6:53 a.m., a private plane unexpectedly flies into the operational area shared by the UAS. The Municipal Water Department and the local television station are operating drones that are connected to ANRA, a USS with a supplemental data service provider that provides surveillance of nearby aircraft via radar. ANRA notifies the operators of the Municipal Water Department and the TV station's drones. The TV station's operator descends to a lower altitude and prepares for landing as a contingency plan, while the water department pilot descends to a lower altitude and redirects its path away from the inbound aircraft. Nearby, another media UAS flies outside the operational volume the operator had specified in the flight plan and is labeled contingent. This unexpected flight path could potentially result in a collision with the public safety drone. Officer Jack Howard, a local public safety official, receives an alert from his USS about the contingent drone that could interfere with his drone's mission. Meanwhile, he uses broadcast remote ID to ensure that the media drone is a legitimate operator. Thanks to the quick coordination of the operators and the remote ID capabilities, the manned aircraft will fly over all UAS operations at a safe altitude as unmanned operations continue with their respective missions.
Use case 2, it begins to inject some of the contingency scenarios or off-nominal scenarios that the traffic management system needs to manage.
What happens if there are changes that occur in mid-flight of an operation or a UAS? We wanted to make sure we're able to address not only the strategic aspects of pre-flight planning, but also when changes arise while an operation is ongoing. In this use case, those types of interactions take place a little bit more frequently in order to address the challenges as operations are taking place in the same environment. Pulling on that thread of de-confliction and strategies to address de-confliction, if those modifications occur as a UAS is in flight, what are the repercussions that has on both operators, and how are they able to de-conflict is one of the key areas that we wanted to explore.
In our particular case, we're demonstrating a few contingency reactions to several phenomena. And those phenomena include, first of all, one of the most important is how we manage interaction with manned air traffic.
Another highlight in use case 2 is the use of a supplementary data service supplier, or we frequently refer to this as an SDSP. These supplementary data service providers provide areas of additional information that may make operations a little bit safer, but are not required. In this use case, there's alerting and avoidance of both manned and unmanned traffic from a third-party source, such as ACAS XU, in order to provide supplementary information to that of the information that's already being shared amongst operators.
It's data that can be utilized by pilots in their planning or during contingencies to better manage those activities. Things like automated weather services or surveillance services. So you might have some ground-based surveillance services that the pilots can utilize to provide the tactical de-confliction. In our case, we'll have a radar deployed during test that's used to detect the manned aircraft. That information is pushed into the UTM system through a supplementary data service provider. The aircraft track from the radar is provided to all of the UAS operators in that area. They utilize that information to adjust and to avoid the manned aircraft to maintain a safe airspace. The second is to demonstrate how the traffic management system manages off-nominal or unexpected behavior from other UAS. It would be one thing if everyone was able to all the time stay in their flight volumes and their pre-planned flight missions. We know that things do go wrong, and so we need to be prepared to manage that. Really what we're talking about is dealing with unplanned behaviors from the UAS. And you might imagine these could be things as simple as an engine failure that causes the aircraft to have to divert from its planned volume, and we need to inform the other operators of the unplanned event and give them the opportunity to respond safely. Other ways that UAS are different than manned aircraft is that they traditionally require a control link. If the aircraft was on a flight path and lost its control link and the pilot was no longer able to control it, this traffic management system would enable contingency management or safe resolution of that anomaly. In our case, we'll be validating the scenario where one UAS accidentally exits its volume and infringes on another operator's volume. The broadcast ID aboard that UAS is going to provide the aircraft's position and notification to others that it is indeed outside of its intended flight area. The other UAS operators are going to then be able to respond and react accordingly. When you say a drone is being flown by a person, there's many different flavors of that, all the way from flying a drone by stick and rudder, so to speak, all the way to a human that's simply monitoring the activity and is there to detect fault and react accordingly. So there's many different levels of automation, so to speak, and many different ways to address that. And the interfaces for the different levels of automation would certainly be different. But at the core of it, they're all leveraging the architecture and the constructs of the unmanned traffic management system. As part of our research, we actually have both of those kind of examples, the manual interface and also the fully automated interface under test during this activity. The state of things now is that we do have the capability to generate even automated response to these contingencies. And as we recognize in many cases, that's actually desirable, because if you can automate the response to this contingency and have a pre-planned contingency behavior, then oftentimes the fault can be alleviated more quickly and more safely. The contingency procedures that are being utilized by industry and UAS operators today are really focused on the core goal of preventing conflict with not only manned aviation, but people and property on the ground, and preventing a failure in the system from propagating to a real problem. And so a lot of these contingency behaviors include things like land now. Simply remove the drone from the conflict is one of the most simple and most basic, but it's also not necessarily the most beneficial with regards to continuing mission and achieving the UAS mission. So the broadcast remote ID, it's really there to address public and public safety concerns and enable them and give them a tool to identify and understand the drone activities in their area.